Hello class, welcome to the video. This video is to make up for the class that we're missing on Friday. We're going to pick up where we left off. We are currently talking about how to determine the right hand or left hand configuration of a chiral molecule, specifically at its chirality center. And what we've gone over is what applies are the Kohn-Ingold Prelog rules. So without further ado, let's do another example where we'll apply those rules. All right, here we have this molecule. We note that this carbon is a chirality carbon because it has four completely different things attached. The isopropyl group, hydroxyl, hydrogen, this is called a vinyl group, the C double bond C. Now, before we proceed though, we have something that is going to be a puzzlement. We've not seen a group with a multiple bond before, double or triple. The question is, how do you handle that? How do you resolve that with respect to the Kohn-Ingold Prelog rules? Well, let me go into that. A double bond is rewritten as follows. The double bond is going to be equivalent to two single bonds. That is to say, this carbon is doubly bonded to another carbon. I'm going to rewrite it so that this carbon is bonded by two single bonds each to a carbon. The carbon that's a double bond will be rewritten and replaced by a carbon with two single bonds, each single bond to a carbon. All right, so let me do the redraw over here. All right. We'll make one single bond to that carbon. We'll keep the structure, well, we're not going to destroy it, modify the structure. So that's one single bond to the original carbon. I need to add a second single bond to a carbon. There's no carbon. I'll add the bond, and then we're going to add in that carbon as a virtual atom, the red symbol C. So you see, this carbon doubly bonded to a carbon is equivalent to the carbon singly bonded each to a carbon, the original, and then the single bond to the add-on carbon, the virtual carbon. All right, this carbon, now in rewriting it is doubly bonded to a carbon, and so we're going to replace this double bond by two single bonds each to a carbon. Well, we already have a single bond to that original carbon. We're going to then add a second single bond, and then we have to sketch in an add-on carbon, a virtual carbon that we will write in red. And that's it. This looks kind of crazy, but rewriting the double bond in this way, this will allow us to prioritize it and apply the Kohn-Ingold Prelog rules. And so now let's proceed. So we're not going to look at this anymore. We really will look at this redrawn structure. Attached to the chirality carbon is a hydrogen, a hydroxyl, the isopropyl group, and this vinyl group. You look at the first attached atom, that's oxygen, carbon, carbon, hydrogen. The group that's obviously the lowest priority is hydrogen. It has the lowest atomic number of all of them. So we're going to then mark this as group number 4, the lowest priority. Oxygen has the highest atomic number of all the first attached atoms, and so it's obvious that this is going to be the highest priority atom, numero uno, number 1. Now the question is prioritizing these two groups. Again, we're not going to look at that, we'll look at this. What is the relative ranking of the isopropyl in our redrawn double bond group? Well, all right, the first attached atom is a carbon in this case. we go to the second tiered atom. We look at the three atoms that this carbon is attached to, and we write them down in order of, well, atomic number first, our highest atomic number first, and lowest atomic number last. This carbon is attached to a carbon, and a hydrogen. And so the second tier of atoms there would be CCH, right? The carbon's first and hydrogen last. The CCH is the second tier of atoms for that group. Now the vinyl group, this is the first attached carbon. We look at the atoms that are directly attached to it. We have a hydrogen and two carbons. And that's the second tier of atoms, right? The carbons first, and then the hydrogen. All right, and there we are. Now we want to compare these two groups. And the one with the a higher priority would be then, therefore, the highest priority group. Now you notice when you compare them, though, they're virtually the same, CCH and CCH. What we have to do in this case is go to the third set of attached atoms, the third tier of atoms. So let's now go ahead and do that. This carbon isn't bonded to anything, so we'll just leave that alone. The hydrogen isn't bonded to anything, so we'll leave that alone. This carbon here is now attached to a C, an H, and an H. And that is our third tier of atoms that I'm going to draw in. So for the third tier of atoms, we'll draw C, H, H. Look closely, hope we're not losing anybody in that. Third tier of atoms, this red carbon and the two hydrogens. Now we'll go back to the isopropyl group. We're going to look at the atoms attached to the second tier of atoms, the C, C, and the H. The C, C, and the H. That's the C, C, and H. The H here doesn't go anywhere, so we'll not proceed with that. This carbon here, which says this one is attached to three hydrogens, so we'll draw them in. This carbon, which corresponds to this, is attached to three hydrogens. We'll draw those in. Right? So in blue, I now have written the third tier of atoms, a string of hydrogens, and then a CHH. Not to worry at this point if they're not the same number of atoms, that's okay. We're still going to be able to compare them and prioritize them. And the idea is that you want to, comparing the groups, you want to look at the first entry first. If it's the same, you go to the next. If it's the same, you go to the next, and so forth. Well, our first entry here is hydrogen, and the first entry is carbon. Carbon is obviously has a higher atomic number than hydrogen. Therefore, this entire group will have higher priority than the isopropyl group. And that is to say, that way when we come out, this will be group number 2, and this would be number 3. All right, now let's just continue. The idea is now you want to view the molecule so that the lowest priority group is away from you, the viewer. One way to approach this is imagine that you're the size of the molecule. You're standing right here so that the H is directly away from you, the viewer. You would be standing right between the hydroxyl group on your left and the isopropyl group on your right. And then pointing vertically would be the double bond group like a flag. Now just redraw that, and you're going to draw a Newman projection formula for that. Draw what your eye sees standing here. And of course I've got the vertical bond to that double bond group. And let me just use the numbers now. That's the number 2. And now standing here down and to your right is the isopropyl group. That's the number 3 priority. And down and to my left is the hydroxyl group. That's number 1. And we're now ready to go. As I say, easy as 1, 2, 3. Start with number 1, then go to 2, and then go to 3. You will either be moving clockwise or counterclockwise. All right, and I am moving clockwise. Therefore, the designation is R, the right-handed configuration for that chirality center. All right, I hope everybody understood that. Let's do some more examples of multiple bonds. And so I think I'll go ahead and erase some of this. everybody gets the idea of this. Suppose we have an attached group, an aldehyde group. Let's say joined to the chirality center here. When you see a multiple bond group, we have to redraw it, following the redraw rules I outlined. All right, in doing that, the carbon doubly bonded to an oxygen will be rewritten as the carbon singly bonded each to an oxygen. So we're going to redraw it as follows. All right, the carbon singly bonded to the original O in blue, and then the second single bond to an oxygen. We have to draw that in, the virtual oxygen, and there it is. Now the oxygen here is doubly bonded to a carbon. That's going to be equivalent to it singly bonded H to a carbon. Well, it's already got the single bond to the original carbon in blue. We just have to add now a second single bond, and then add the add-on oxygen for that, the virtual oxygen. And it looks crazy, but this will indeed work and allow you to prioritize that aldehyde group. And now, the piece de resistance, I guess, let's try a triple bond. Suppose you had a triple bond carbon group attached to the chirality center of this. All right, how would you redraw that? All right, the triple bond is going to be redrawn, replaced by the carbon singly bonded each to a carbon. Triple bond is equivalent to the carbon singly bonded each to a carbon, so let's proceed. All right, the carbon here, we're going to write one single bond to the original, preserving the structure, and then we have to add two additional single bonds, and each to a carbon. There's one bond, and we have to add in the C symbols, the virtual carbon here and here. And we have to finish it up. That carbon is strictly bonded to a carbon. That will be equivalent to it singly bonded each to a carbon. Well, you already have one single bond to the original. We just have to add in two more single bonds and add in two virtual carbons, and there it is. Crazy as it looks, this rewritten structure will allow us to prioritize it. All right, and now we have one additional thing, shifting gears a bit. I want to show you a couple of models. There is one feature, one property that chiral molecules have that I want to draw attention to, and then we'll expand on this a little later. We have these two models. A little light on the situation here. Now, there's a central carbon. This carbon, let's look at one, is a chirality center. You could call this chlorine, this iodine, hydrogen, and then an OH group. These four things are different. That makes this a chirality center. We have this model. This has the same four groups attached, the OH, the green chlorine, and the violet iodine and yellow, and two possibilities. Either these are identical or they're mirror image isomers. Well, the way to test to see if they are identical is to see if they superimpose, to see if the like groups coincide when you bring them together. And let's see how that's going to work here. Okay, so we got OH and the green, and now I can bring these together so that the green and the hydroxyl groups overlap. You see that? The green and OH fall together. But notice there's a mismatch between the violet ball and the yellow ball, between the iodine and the hydrogen. They don't superimpose. That means they're not identical. They're isomers, specifically. They're mirror image isomers. They're enantiomers. And what I'm leading up to is the following. These are enantiomers, but there's a very important, interesting property. If I take one of the enantiomers and I interchange any two groups, any two, it doesn't matter, I will show you that I will convert that to the other enantiomer. So let me take and interchange the green and the yellow, hydrogen and the chlorine. And now, if what I said is correct, these molecules are identical, and we'll do the superimposability test on it. And okay, lined up like this. Indeed, I hope you can see that when you bring them together, they will coincide, the like groups coinciding. They are superimposable. All of the balls and the groups will coincide. And that's an important property. If you have a chirality center interchanging any of the four groups, interchanging any two of the groups, will convert it to the enantiomer, and that's an important property of chiral molecules. All right, that's all for this part of the video. The next part of the video, you'll hear my voice and me working with drawn structures or drawing structures. Bye.
Welcome to part 2 of the video. We've been examining chiral molecules that contain one chirality center. Let's take a look at molecules that have 2 or more chirality centers. All right, let's consider this structural formula. Alright, now this is a structural formula, it's not a specific molecule. Alright, now in this structural formula, the key question is, how many chirality centers does it have? There are 4 carbons. We have the CH3, that's not a chirality center, obviously, there's 3 like hydrogens. On the second carbon we have a methyl, a chlorine, a hydrogen, and this large group. All 4 things are different, therefore this carbon will be a chirality center. And we'll put a star there. The second carbon has this large group, the hydrogen, the bromine, and the methyl, 4 different groups. So that's a second chirality center, which we will star. Now our task is to find all of the possible stereoisomers for this structural formula. All right, here is a 3D formula for one possible stereoisomer. Now notice that we're using a 3D wedge formula to represent it. And there's also something important about the way that it's drawn. The way that I've drawn it conforms to a standard convention for writing the formulas of open chain molecules that have chirality centers along the parent carbon chain. The idea here is to orient the molecule vertically so that the parent carbon chain is actually curved, that is, bowed toward the viewer. This means that one end at the top points away from the viewer and the other end at the bottom points away from you, the viewer. Now we could continue our search for other stereoisomers using these 3D wedge type formulas, but doing so will be difficult because it requires visual manipulations in 3D space. In the 1800s, the pioneering organic chemist Emil Fischer was working with structures of sugar molecules. Sugar molecules have multiple chirality centers. To make the drawing of such structures easier, he introduced a new kind of formula. It's called a Fisher projection formula. Now remember that a projection formula is a two-dimensional drawing of a three-dimensional object. That was the case with the Newman projection formula. Let me explain the Newman projection, or rather the Fisher projection formula. We have our 3D wedge formula oriented vertically. The parent chain is oriented vertically. We're going to draw what corresponds to that, simply a vertical line. All right. For each chirality center, we'll draw a short horizontal line segment, like this and like this. So the intersection of the vertical line and the horizontal line segment corresponds to a chirality center. This intersection would correspond to this chirality center, and this intersection would correspond to that bottom chirality center. Then we can just simply complete the molecule. We've got a CH3 here at the top. We have a CH3 at the bottom. Now we don't care about the three-dimensionality of the CH3 group. Remember, this is a two-dimensional drawing, so we'll just simplify and write it as CH3. All right, now in our original drawing we have bromine on the right, hydrogen on the left, and we'll accordingly write Br on the right, H on the left. For this chirality center, we have chlorine on the left and a hydrogen on the right. All right, this is the Fisher projection formula for our starting molecule, one of the possible stereoisomers. All right, now let's continue. What we're going to do to find the others is, well, this. Let's draw the mirror image of our first stereoisomer. In fact, let's call that Roman numeral 1. All right, here is a vertical dashed line, represents a mirror, and we draw the mirror image reflection. This becomes easier to do for the two-dimensional Fisher drawing. Methyl and methyl. All right, here, this is the mirror image of number 1. If they were superimposable, we would just have redrawn number 1. But if it's not superimposable, my second drawing will be the enantiomer of number 1. Well, we need to test for the superimposability. That's something we're going to have mentally do, but it's easier to do in 2 dimensions than 3. We'd simply take this molecule and slide it. You can see they don't superimpose. If I were to rotate, then it would not superimpose. The idea of the Fisher formula is that when you're comparing 2 structures, you're only allowed to slide and rotate in the plane of the drawing. You're not allowed to flip it over like a pancake, because that would be entering the non-existent third dimension. And believe me, this makes the comparison of structures much easier. So indeed, if we take our second drawing, slide, rotate, it won't superimpose. We have a number 2 that is the enantiomer of number 1. All right, well, Well, let's proceed. We're going to find additional stereoisomers, and the way to do that is as follows. Let's keep the configuration of this top chirality center the same. We're not changing that. But let's change the configuration of this bottom chirality center. The simplest way to do that is simply interchange the hydrogen and the chlorine. And that's now what I'm going to do. So here is my keeping the top chirality center configuration the same. Get the CH3, and we're interchanging the Cl and the H for the bottom one. All right. All right. Now there's my third drawing. This will be a third stereoisomer if it's not superimposable on either 1 or 2. Now if you take and slide and rotate in the plane of the drawing, again you're not allowed to flip it over, you can see, I think all of you can see that this third drawing doesn't superimpose. It's actually a third stereoisomer. I'll label it therefore Roman numeral 3. All right, let's do like we did for the number 1. We're going to draw the mirror image of number 3 to see if we can find a fourth stereoisomer. So I'm just simply drawing what my eye would see as the mirror image. All right, like that. The H is there, and the Cl is there, and the CH3, and the CH3. Okay. Now let's test the superimposability of my new drawing with 3. And you can see that, well, let's see if I slide them over. No, they're not going to line up. If I rotate 180 degrees in the plane of the drawing, and nope, they won't line up. Indeed, my fourth drawing is a fourth stereoisomer. We'll label it number 4. All right, that's all of the stereoisomers. In total, there are 4 stereoisomers for my starting structural formula. I didn't mention it, but in fact I should have done so. There are 2 chirality centers here that you can see in the original structural formula. This is a chirality center, and that's a chirality center. There are 2 different chirality centers, and this will lead to 4 different stereoisomers. All right. Now, let's ask some key questions here, though. We have 2 pairs of enantiomers. 1 and 2 are enantiomeric pair. 3 and 4 are an enantiomeric pair. 2 pairs of enantiomers. But what's the relationship of 3 to 1, of stereoisomer 3 to 1? They're different. They're not superimposable, obviously. They're not mirror images. They're not mirror image isomers because 3 and 1 are not mirror images. So what kind of stereoisomers are they? Well, in fact, it sounds trivial, but they're referred to as non-mirror image stereoisomers. 1 and 3 are non-mirror image stereoisomers. Now there's a technical term. They're called diastereomers. Now let's look at number 4. What's the relationship between 4 and 1? Well, they're different. They're not mirror images. They're not mirror image isomers. They're also non-mirror image isomers, or diastereomers. 1 and 4 are diastereomers. 2 and 3 are also diastereomers. 2 and 3 are diastereomers. And 4 and 2 are also non-mirror image stereoisomers, that is to say, diastereomers. New term, diastereomers. It's simply a synonym for non-mirror image stereoisomers. Now, to make this a little clearer, I want to now look at a chart we've used this chart before, and this describes the different categories of isomers. The heading of this is isomers, and we know at this point that there's two main classes of isomers: constitutional isomers and stereoisomers. At this point now, well, we've learned that there are geometrical isomers and mirror image isomers. To flesh this out more and make it more detailed, we really have this. Stereoisomers fall into two categories: the mirror image stereoisomers and the non-mirror image stereoisomers, or diastereomers. Those are the two subcategories of stereoisomers: mirror image stereoisomers, also known as enantiomers, and non-mirror image stereoisomers, also known as diastereomers. Now, we've already learned about geometrical isomers. If you think about it, geometrical isomers are non-mirror image stereoisomers. Are cis and trans isomers mirror images? Well, no. They're stereoisomers, therefore we could call them non-mirror image stereoisomers. You see, they're a subcategory of diastereomers. Now, what we just looked at previously, Roman numeral 1, 2, 3, and 4, those stereoisomers, the 1 and 3, for example, the diastereomers, they're not. We can't call them. We can't call them geometrical isomers because there is no double bond or ring. They're not cis-trans isomers. And so, to be honest, chemists don't have an official name for them, but I'm referring to them as multi-chiral center diastereomers. Multi-chiral center diastereomers. The diastereomers that we listed previously, if you recall, 1 and 3, 2 and 3, and so forth, would be diastereomers that would fall in the category multi-chiral center diastereomers. There is no double bond or ring to them, and so that would be an appropriate term. Okay, returning to the 4 stereoisomers that we found for our starting structural formula that had 2 chirality centers, I want to ask some key questions regarding their physical and chemical properties. All right. Let's compare 1 and 2 with respect to physical properties. They're enantiomers. Well, the answer is they're the same melting point, same boiling point, same density. The only exception is the sign of their specific rotation. 1 and 2 are enantiomers. The physical properties are the same with the exception noted. Their chemical properties are the same with the exception we noted in class. The rate at which they react with a given chiral reactant is different. Let's ask the similar question with respect to stereoisomer 1 and 3. Now they're diastereomers. 1 and 3 are diastereomers. What about their boiling points? Well, they'll be completely different. They are not mirror image isomers. They have really different configurations, and their average attraction between molecules in liquid state would be different. Their melting points would be different. They would have actually different densities, and so forth. And we come to an important generalization that diastereomers have different properties, both chemical and physical. Diastereomers have different properties. Have different properties, both physical and chemical. Enantiomers have basically the same properties, but diastereomers are completely different. All right. Another question. Is isomer 1 optically active? The answer is yes, it is. It's a chiral molecule. Is isomer 2 optically active? Yes, it is. It's a chiral molecule. All of these stereoisomers are in fact optically active because each is chiral. Each one has a mirror image that's not superposable. And if a molecule is chiral, then it will be optically active. All right, I want to do another example of a molecule that has more than one chirality center. So let's work on this structural formula. All right. Now the question to ask is, where are the chirality centers? When we find one, we'll put a star on it. The methyl group is not a chirality carbon, so no star. This carbon has a methyl, a bromine, a hydrogen, and this big old group, and that carbon is a chirality carbon, so we'll star it. This carbon has a hydrogen attached, a bromine, a methyl, and this large group. All those four groups are different, so that's a chirality center, and we'll star it. The last methyl carbon is not a chirality carbon. So this structural formula has two chirality centers. But our task is to find all the stereoisomers, but before I do, I want to call attention to this. How is this example different from the first one? On the first one, we had a bromine and a chlorine, two chirality centers. This one, we have two bromines. If you make a list of the four things attached to each of the chirality centers, that list is the same. Both chirality centers are indeed chirality carbons. They have four different things, but the four things that each has are the same. Therefore, we will call these equivalent chirality centers. In our first example, with the chlorine and the bromine, those two chirality centers would be non-equivalent chirality centers. All right. Now, to find all the stereoisomers, we'll proceed as we did before, using the Fisher projection formula. All right. So I'm just going to choose one. This. Let's call this number 1. This indeed is one of the possible stereoisomers. All right, we'll proceed as we did before. Let's draw a mirror and draw the mirror image. Okay. Whoops. That's not the mirror image. The BR here is closer to the mirror. The mirror image, the BR, would be closer to the mirror. All right, and then the CH3, and the CH3, and then we have the hydrogen, and we have the bromine. Do be careful when you're drawing the mirror image to make sure you have the correct mirror image. So let me double check. The BR and the H on number 1 are closer to the mirror. So in the second, or in the mirror image, we want BR and H to be close to the mirror. All right, now we want to see if these are superimposable. And remember, with the Fisher formula, you're not allowed to flip it over like a pancake. You are restricted to sliding and rotating in the plane of the drawing. And that's a good thing, because it's easier to do that rather than trying to visualize the molecule in 3 dimensions, having to turn or manipulate the thing in 3D. So if we take this mirror image and we slide it over, you can see, I think, that it doesn't superimpose. If I were to rotate this image 180 degrees, this BR here would fall where the hydrogen is, and so forth, and they don't superimpose. So we have found an enantiomer. This is our Roman numeral 2 is an enantiomer of number 1. All right, now we'll proceed as we did before. We're going to find a third stereoisomer. Let's keep the configuration of the chirality center at the top the same, but we'll change the configuration of the chirality center, this second one, by interchanging the bromine and the hydrogen. Interchanging the bromine and the hydrogen. All right, so keeping, we're working on number 1. So you want the hydrogen here, methyl, and then bromine. And I want to change the configuration of that. And I'm going to interchange the H and the BR here, so I will do that now. And there's my CH3, and now here's a third drawing. Is this a third stereoisomer? Well, if it's not superimposable in 1 or 2, the answer is yes. And if you check, you'll see that it's not superimposable. We have found a third stereoisomer. We'll label number 3. All right, and proceeding as we did before, let's draw the mirror image of number 3. BR, H, methyl. All right. Now, the customary procedure is, when you've drawn the mirror image, test to see if it's superimposable. All right, so let's do that here. If I take my drawing here and slide it over, they don't line up. But if I take this and rotate it 180 degrees in the plane of the drawing, voila, boom, they do superimpose. So this mirror image is just Roman numeral 3 redrawn. It's not a fourth stereoisomer. All right, and now we have it. There are only 3 stereoisomers for our starting structural formula, the one that has 2 equivalent chirality centers. We have a pair of enantiomers, number 1 and number 2, and then we have a third stereoisomer that we label number 3. Okay, now number 3 has some interesting features that I want to call attention to. Let's examine number 3. Well, let's, as a lead into that, let me ask a question. Compound number 1, is it optically active? Well, it is chiral because its mirror image is non-superimposable. So one is optically active. 1 is optically active. All right. 2 is optically active. It's the enantiomer of 1. 1 and 2 would have the same specific rotation but be opposite in sign. I don't know which is negative, which is positive. You'd have to introduce it in the polarimeter to tell. Now we come to number 3. The key question is number 3 optically active? Think about it. Well, there's a couple ways to look at this. Number 3's mirror image is not superimposable on the original. That means that 3 is achiral. 3 is achiral. Now remember, a chiral thing, one definition is that its mirror image is not superimposable. If the mirror image of something is superimposable, then it's achiral. 3 is achiral. Now if it's achiral, it's not optically active. So 3 is optically inactive. Moreover, you can, if you look at it, you can also see that number 3 has a plane of symmetry. If I bisect the molecule down the middle, the upper half is the mirror image of the lower half. It has a plane of symmetry. Anything that has one or more symmetry elements is achiral, and its compound would be optically inactive. Now, stop and think of what we have. We have actually kind of an ironic situation. Number 3 has 2 chirality centers, yet overall it's achiral. The molecule has 2 chirality centers, and yet it is achiral overall, optically inactive. When we have a molecule with that feature, when it has multiple chirality centers and yet is achiral overall, we call it a meso compound. 3 is it's a new term now, meso, M-E-S-O compound. Or we also can say a mesoform. And it's important to think about this. This is a new term. It's a new type of molecule. And again, to define it, a meso compound is one whose molecule has multiple chirality centers and yet is achiral overall. All right. Okay, to just finish this out, 1 and 2 are enantiomers. What's the relationship between 3 and 1? They're diastereomers. 1 and 3 are diastereomers. And 2 and 3 are diastereomers. 2 and 3 are diastereomers. All right. That basically concludes the video. there may be a second video depending on how much time I have remaining. Thank you for watching. Goodbye.